Welcome everybody to the Rocky Mountain Mathematical Physics Seminar. Our speaker today is Albachiara Cogo from the University of Tübingen, and she will speak about black hole and equipotential photon surface uniqueness in n+1 dimensions via Robinson's method.
So
welcome.
Thank you so much for having me, and I'm very happy to present this joint work that has been on archive for a couple of weeks now, and I did it with Professor Cederbaum, Professor Leandro, and Professor Dos Santos. So I'm going to start. So I'm going to talk about the famous black hole uniqueness theorem, and maybe it's a new topic for most of you, the uniqueness also of equipotential photon surfaces. And the method is going to be this Robinson, which we are going to see what it has to do with. So let me do the setup of the problem and state it in a verbal way. So we study solutions, which I'm going to call n+1 G. So Lorentzian manifolds with a time function in any dimension. Of the vacuum Einstein equation, which is Ricci of this spacetime being totally zero in the whole manifold. So this is our first feature that we have to remember. So we are in vacuum. I'm trying to keep track of all the details. Okay, so we are in vacuum. And then we also required that the solution is standard static. And this means that basically the spacetime Riemannian manifold, which I'm going to call mg. So the g bar will be the metric, the Lorentzian metric, and the g little g will be the Riemannian metric from a basically time slice. So we have a Riemannian manifold with a compact boundary. Okay. This in parentheses, and a function which is smooth on this Riemannian manifold, which is positive in the interior. And in physics is called lapse function because it measures somehow the ticking of the time, such that we can split our space-time as a product of the time coordinates, which runs in R. Okay, this G is the G of the Riemannian manifold. Okay, so we have vacuum, standard static, and the third feature is asymptotically flatness. Okay, so there exists a chart for our manifold outside a compact set. So this K will be a compact set. Let me write it in another color to remember. Compact set. Okay, so if we remove a compact set of our manifold, there exists a chart which maps it to Rn minus a closed ball. And moreover, so this is the third feature. Okay, so this is the picture that we have. So, okay, one can have this picture in mind. The light green area will be the one we are interested in, and is mapped to Rn minus a ball, and the main feature that we want to ask for is that the metric in that area approaches, so this is the push forward of the metric in by this chart, will be the Euclidean metric plus an error. I will write O2 and maybe explain what it means for the ones who have some expertise on this. So we approach the Euclidean metric at this rate that I wrote. So this O2 means that up to the second derivatives, we go like 1 over x to the power tau. And this tau, in our case, will be greater or equal than 0. And then one takes it to be less than n over 2 because otherwise, I mean, it doesn't make sense because the mass will be 0. Okay, this is a technical thing about the IDM mass. But so we approach the Euclidean metric at a relatively fast rate. And in particular, in our case, we can take tau equal to 0. This is important to compare our proof to other proofs. Okay, but it's not the most important thing. What you have to remember is this picture that maps the spatial infinity to Rn minus a ball. So, okay, to summarize, we are in vacuum, we have a standard static solution and an asymptotically flat solution. Okay, and we studied this in this setup, a solution that has so in presence of a black hole horizon or an equipotential photon surface. Okay, so in the splitting of our space time in a spatial part, which is going to be this M. This is the spatial part. So these are going to be, the M represents the time slice. So in M, if we restrict to a time slice, the photon surface in the equipment or the black hole horizon are going to be the boundary. And we are going to see it later why. Okay, so you have to think of this boundary here in this picture to be an horizon on an equipotential photon surface. Then the uniqueness theorem says the following, that in presence of this object, then the whole manifold is rotationally symmetric. So we have a sort of super strong rigidity statement. And in particular, I'm going to mention it later, this means that the manifold is the Schwarzschild spacetime. Okay, so this is the verbally what we want to prove. Under this condition, under this strict condition that I mentioned before, and in presence of objects like a black hole horizon or equipotential photon surface, we have rotational symmetry. And I'm going to formulate right now the problem in terms of PDEs. So somehow with this rigidity statement, we have a uniqueness of a solution of a system of PDEs. So let's see what we have. So due so we have the staticity of the problem. So due to the staticity of the problem, we can forget about the space-time and just think about the slices. So we can just study tuples, so mg, and the lapse function. So we have a one-to-one correspondence between this and the whole space-time, satisfying the static Einstein equation in vacuum. So if we rewrite the Einstein equation, which is Ricci equals 0 of the spacetime metric, in terms of the time slice metric, we find the following system, which I'm going to call static vacuum Einstein equation, SVE. So F times Ricci, this is the Ricci of the time of this spatial metric, G, is the Hessian of F in M. The Laplacian of F vanishes in M. So these are the static Einstein equation. And okay, so of course, this, as I said, this Ricci, this Laplacian, and this Levi-Civita are the geometric object related to G of the Riemannian, so the Riemannian metric G. Okay, and okay, so reformulating the problem mathematically, we have to solve this system of PDEs with the boundary values f equal f0, so a constant, positive, non-negative constant on the boundary. I'm going to use this color for the boundary again. Okay, and then we prescribe, of course, this is a second order. I mean, we have a Laplacian of f, so we prescribe also another boundary condition, which is going to be at infinity. So in this picture, we will have on partial m in the boundary here a value of f, and then we will have a value of f as approaching infinity. So f at infinity will be 1 up to errors. So I'm going to say what this is, this m. So it goes to 1 at this rate. Okay. As we go to infinity in the chart that defines the asymptotically flatness, and this is going to be our problem. This m that appears and gives the first rate of convergence to 1 of f is just a parameter that in this talk will be positive, but will be just a real parameter. And okay, just an observation: if the tau in the decay rate that we had here, this tau, is greater than n/2/2, then one has that the eigenmass is well defined, and m will actually coincide with the eigenmass. Okay, just for information. And we will call a solution MGF solution to this system, sorry, to this problem, a static solution, static system, sorry. Okay, I'm writing all of this because I will be using this terminology. Okay, so this is the mathematical setup. And okay, if one wants to impose from the beginning rotational symmetry, and one tries to solve this system of PDEs, one can find the Schwarzschild solution. So actually, we have that the unique rotationally symmetric solution to unique up to up to fixing the mass. So is the Schwarzschild solution. So it's actually the unique solution to the problem because we have to fix the mass, namely this decay at infinity. So it's a Schwarzschild solution of mass m. Okay, and the Schwarzschild solution will be a manifold given by this product. So we have an interval from 2m to infinity, the unitary sphere, and the metric will read as follows: 1 over n squared dr squared plus r squared, the standard route metric on Sn minus 1, where the r coordinates is the radial coordinate taken in this interval. Okay. And n is the Laplace function. So, okay, I'm calling it n because I'm used to this notation, but in the notation above, n will play the role of f. So this Laplace. Okay, so n will be 1 minus 2m over Rn minus 2. Sorry. Okay. So just to say, this plays the role of f in the equation. Okay, so this is the easiest example, or like the easiest non-trivial solution to this system. Okay, of course, if one takes m equals 0, one has also a solution which will be Minkowski. Okay, so it's a trivial solution. Okay, okay, so this is the setup, and as I said before, we want to show that actually, if I prescribe the boundary simply being a black hole and an equipotential photon surface, then I must be Schwarzschild. So this is a very strong statement. I just underline it. Okay, so let's talk about these objects that I introduced in verbally, so the static horizon and the photon surface. So with static horizon, I will simplify the solution being the following. So if we take a static system, as before, we say that the boundary is, so I'm going to work in the time slice, is a static horizon if this lapse is 0 at the boundary. For people who work with Killing horizon, this corresponds to having a Killing horizon in the whole space-time, because, as we said, f is the Laplace function. So, okay, maybe I will write a Killing horizon in the whole space-time, because somehow f squared is the norm of partial t. So, okay, sorry. So if it goes to where it goes to 0, we will have a Killing horizon, which is exactly the case that I described, restricting to a time slice. Okay, and Killing static horizons, let me underline this, have some properties which will be crucial in proving the uniqueness theorem that I mentioned. So they have surface gravity constant, and the surface gravity in this case will be the norm of the gradient of f restricted to the boundary, constant. And they will be totally geodesic, and okay, because they are static. So the second fundamental form vanishes, and then in particular they have also Zino-mean curvature, so they are minimal. This follows from, actually, both of these things follow from the first, I think, yeah, I wrote it first, the first static vacuum equation. So if you try to write the second fundamental form, for example, of your horizon will be related to the Hessian of f, because it's the level set of f. And then you will see that since f goes to 0 at the horizon, you will have that it vanishes. Okay. Okay, so static horizons have these very strong properties, and one can use them heavily to prove the uniqueness theorem. Let's see now what are photon surfaces and which are their properties, and this will explain why these two objects can, give this uniqueness theorem, both of them. So, photon surfaces, I just want to underline that now, okay, so far we have been kind of working in the time slices, and now to define photon surfaces, we have to go back to the whole spacetime. So the definition is in the whole spacetime. And I will provide some pictures to make it clearer. So photon surfaces, so a photon surface is an embedded hypersurface, sorry, which way? Hypersurface, which I'm going to call P, and in the spacetime with the following features is time-like, which means that if we restrict them, so the metric induced by the spacetime is still Lorentzian, or equivalently, the normal is always strictly space-like. So induced metric is Lorentzian. And is also totally ambiguous. Okay, which means that the second fundamental form is proportional to the metric.
Albachiara, totally what? Sorry, I don't understand that.
Yeah, sorry.
The
Yeah,
word
also
there. Thanks.
terminology seems not to be shared by all the community. So yeah, umbilic. So that's the way I'm used to define this, but it simply says that the second fundamental form is proportional to the metric. Yeah.
Thanks. I have no objections to the term at all. I just couldn't read the word. Yeah,
No,
thanks.
because I already encountered I already encountered
some objections
that didn't use this word, and so I think it's not shared by the whole community. Yeah.
Thanks.
So it simply means this. But the interesting thing is that, and that's how I would define them usually, but yeah, this is just easier to remember that it's totally umbilic. Okay, or another way to see it is that the trace-free part of the second fundamental form vanishes. I will write it like this. But the interesting thing is that this corresponds to be null totally geodesic. Okay, so what does it mean? That the null geodesics that are, the null geodesics of the photon surface are also null geodesic of the ambient, which means that if a photon at some point is tangent to our surface, then it gets trapped. And so somehow these objects are interesting because the light is trapped on those. So this is, physically speaking, means that the photons are trapped. And a photon surface is equipotential, which is what we are interested in, if the lapse function is constant on connected components of its time slice. So connected components of the time slice. So if I take the intersection of my photon surface with a time slice, which I'm going to call MT, then the lapse function must be constant there. And if, okay, F is constant. And if F is constant, no matter which time slice I take, independently of T, then P is a photon sphere. And I mentioned this because photon spheres are very important objects in physics. And I'm going to say a bit later why. And another physical intuition that I want to mention is that if F is constant, it means that we have a constant, so the photons have constant frequency on the time slices. Or energy, equivalently. Okay, so it's a sort of, I mean, it's really strictly related to energy. And in fact, especially photon spheres are very important for energy estimates, also in the hyperbolic, for the hyperbolic community who studies stabilities and so on. So these are objects that are studied also for other reasons. Okay, so here I have a picture, and just want to say that, okay, in Schwarzschild, maybe I can restrict to the n equal 3 case. In n equal 3, the horizon is at radius equal to m, and the photon sphere, sorry, is at r equals 3m. So you really, in Schwarzschild, the photon sphere can be visualized as in this picture as a sort of cylinder somehow, because it's at a fixed radius. And you can see, okay, from the picture, to keep in mind what happens is that the light, which follows this null geodesics, is trapped on it. Okay, I hope this picture can be good enough. Or another way to visualize it maybe is this one, in the sense that yeah, so somehow the famous black hole picture from MIT. So somehow what we see is actually the photon sphere, which in this case will be, I mean, I think we know, okay, this is I'm not an expert on that, but what I will say is that this is the case of Kerr, the Kerr photon sphere, or because this is the best approximation that we can give for our universe, in our universe, sorry. And we see the light because the photon sphere is unstable in Kerr. Yeah, but so this kind of annulus where the light is trapped is actually a good way to remember the photon sphere. Okay, so let me say, okay, before I said, okay, we have mentioned the static horizon with these properties, and now we want to see which are the properties of the photon surfaces, and yeah, that we will use in our proof. So let's consider a static system. And then, so now let's restrict to a time slice. So here we will just restrict to one of the time slices M. And let the boundary be a time slice of an equipotential photosurface. Okay, then we have the following properties. So first of all, again, the surface gravity is constant. So it's the norm of the gradient of F, sorry, constant. But then before we had a minimal surface, now we have something else. We have umbilicity, which means that the traceless part of the second fundamental form vanishes, or equivalently that the second fundamental form is proportional to the metric, also in the time slice. Totally umbilic. Okay, and an additional feature, which is that the scalar curvature and the mean curvature are constant on it, and are related by the following identity. Okay, I mean, it's not very important to have it in mind, but it's just to say there is a formula which relates all these constant quantities, and this is very important to conclude the proof. Okay, this basically, okay, you can think of it as the Gauss equation, nevertheless. Okay, so this is just a translation of the Gauss equation for photon surfaces, and to see the proof, I mean, or more details on photon surfaces. I mean, there has been a lot of research on that. I will give you this reference. So Cederbaum, Jans, and Martinez. Sorry. Okay. Okay, so now let's try to state the uniqueness theorem in more precisely. So let's again have a static system. So this Riemannian manifold and this lapse function, which is asymptotically flat. Which is asymptotically flat and solves the problem that we mentioned before. And suppose that the, I forgot a bit to say, but it was clear, I guess, from the picture, is that this picture, is that the boundary is going to be contained in the compact set that we remove to have the asymptotically flat chart. Yeah, that is, it was clear, I think, from the picture, I hope. So suppose that the boundary, I keep the color, is a black hole or a static horizon, or a time slice of an equipotential photon surface. Okay, I've already written it because it's not important to have everything in mind, but so then one can have this lower and upper bound from M. And if you remember this, this M, I'm going to redo it. This M was the parameter that appeared in the expansion of the lapse at infinity. So here. Okay, which is the eigenmass of the system in particular, we have this lower bound, which corresponds in the case of the horizon. So where F is, sorry, and also in these formulas, I'm writing F, sorry, I'm writing in blue the quantities that will vanish in the case of the horizon. So they appear only for the equipotential photon surface case. Okay, so if you notice this lower bound with F being 0, so the case of horizon corresponds to the famous Penrose inequality. And instead, the upper bound, you see, is given by, again, similar quantities. So the norm, so this quantity here, sorry, this is the volume of the boundary. And this is the standard volume of the unitary sphere. So these are quantities that appear also in the upper bound. And then we have somehow, in the case of horizon, because this quantity vanishes, we have an upper bound of the mass given by the integral of the scalar curvature. Okay, so this is just an observation, and we will see later why these inequalities matter and why they correspond to the uniqueness theorem. So now I'm saying, if equality holds here, in particular, okay, this is implied if I have an upper bound on the integral. So if you see that if I have this upper bound on the integral of the scalar curvature, I have that the equality holds in both sides. So I will have equality instead of inequality, sorry. So, okay, if we have this upper bound on the integral of the scalar curvature, then we have equality. In particular, this corresponds in 3 dimensions to Gauss-Bonnet. In higher dimension, we don't have Gauss-Bonnet, so this has to be assumed. But if equality holds, then, sorry, equality holds if and only if we have the Schwarzschild spacetime or rotational symmetry equivalently. Okay, so in this sense, we have uniqueness. The uniqueness theorem. Sorry. Okay, so this theorem, not exactly stated like this, but just saying if I have a static horizon in a static space-time then we are Schwarzschild, has been already proven in different fashion with different assumptions. So this is a kind of historical overview. So for the black hole, the first one in 3 dimensions was given by Israel, as you can see, in the 67. And then, so as we said, the properties of the black hole, so black holes have properties, but also equipotential photon surfaces. So sorry, with black hole, I mean the static horizon. So static horizon have the properties we mentioned before, and equipotential photon surfaces have other properties which, with some more work, can replace the one of the static horizon. So the proofs can be sort of adapted from the black hole case to the equipotential photon surface case, and you see a correspondence in the lines here. Okay, so the Israel proof has been adapted by Cederbaum to actually photon spheres, but I'm going to include everything in this tab. Then the static horizon has been proven by Robinson in 3 dimensions, which is the one we are inspired for the higher dimensional case. And then by Banting and Mazzudola-Lam in the 87. This has been adapted by Cederbaum and Galloway for the equipotential photon surface case. And in higher dimension, there were many proofs. So the first two, I kind of made groups in terms of colors. So the light brown will be all the proofs that are inspired by Banting and Mazzudola-Lam. So this Hwang, Gibbons, Ida, and Shiromizu's proofs were inspired by Banting and Mazzudola-Lam. And they have different assumptions, for example, the spin assumption or a very strong decay. And then, yeah, there has been other proofs by Nozawa, Shiromizu, Izuni, Yamada, Agostiniani and Mazzieri with another method. And all have been also, I mean, almost all have been adapted to the photon surface case. So in this talk, I'm going to talk of our adaptation of the Robinson proof in higher dimension. Something that has to be said is that, okay, why people keep trying to prove it in different ways when it has been proven? Because there are, as I said, there are different assumptions in the different cases. In particular, in the first one in Israel, one assumes that the Lab function is foliating the manifold, which is a super strong assumption that has been removed from almost all the others. And in general, the Banting and Mazzudola-Lam method is the best somehow so far. Why? Because it admits multiple connected components. So I forgot here to mention that this boundary has to be connected. This is a very strong assumption that we have to make. So apart from the Banting Mazzudola-Lam, all the other methods have to assume connectedness of the boundary. They don't. So this is very strong in that. I mean, this is a very strong proof in that sense. But a thing that we have to say is that they use the positive mass theorem. And the positive mass theorem requires stronger assumption on the decay, and also, I mean, has some restrictions somehow in the dimensions, and is a very strong hammer somehow. Yeah. And just to mention, for the sake of mentioning, these proofs have also been adapted to more general matter models. For example, people have been working on electrovacuum and other situations. But yeah, let's restrict to the vacuum case here. Okay, so I'm not mentioning all the literature outside the vacuum case. Okay, so the important thing is that the main idea of all the approaches, apart from the Banting Mazzudola-Lam, is the following. It's very easy to say. So take a vector field or a family of vector fields, but okay. We take a vector field in M such that its divergence is non-negative and is 0 if and only if mg is rotationally symmetric. So somehow in the so somehow this divergence has to encode some tensors or some quantities that detect rotational symmetry. And all the methods have different way to detect it. We are going to see in our method what we use. And then we use the divergence theorem to transfer the problem to the boundary. Okay, so yeah, so we are, okay, in general, we are proving a rigidity statement for the whole manifold. And to do that, we want to show that this divergence is zero. And to show that the divergence is zero, we are going to use the divergence theorem to just use the properties of the boundary and get equalities in the divergence equation. Okay, so let's see what Robinson did in the black hole case in 3 dimensions. Okay, here I have written some formulas, but it's not important to, I'm going to observe only some quantities. So it takes a family, a 2 parameters family, it takes of vector fields. So here, just for the sake of mentioning, I just wrote down, so we have a function that depends on 2 parameters A and B in real parameters that has to be positive because we want this divergence of the vector field to be positive. And then, okay, it takes this vector field, which doesn't matter. I mean, the form doesn't matter right now, but the important part is that the divergence here, so let's compute the divergence, is non-negative because we require this function f, big F, to be positive, and is zero if and only if these 2 quantities vanish. So this is the only thing we have to keep in mind. So the divergence of the family of vector fields that he has is zero if and only if these 2 quantities are zero. Okay, the quantities in blue are zero. Okay, and then what it does is like, okay, it detects rotational symmetry via these 2 equations, and it concludes rotational symmetry. Okay, actually in 3 dimension, maybe I will mention it later, but in dimension 3, these two equations, so these 2 quantities being zero, are redundant. So actually one needs only one of them. So okay, then the goal restricts to show that this divergence is zero. So once one is able to show that if these 2 quantities gives rotational symmetry, then the problem restricts to show that this divergence is zero. And as we said, one can use the divergence theorem to transfer the problem to the boundary and use the properties of the boundary. And here, sorry, I was giving for granted the C tensor appearing in the second term is the Cotton tensor, which is like, I mean, you can think of it as a derivative of the Ricci. Okay. Okay, now what about the higher dimensional case? So in the 3-dimensional case, we see that the Cotton tensor appears, and the Cotton tensor is a very 3-dimensional object in the sense that we know that in 3 dimensions, the Cotton tensor captures the local conformal flatness. So if one thinks of generalizing this method to higher dimension, well, one can think of the Y tensor, for example. So, okay, the question would be, how we replace the Cotton tensor in higher dimension. Sorry. And, okay, the local So for example, one can guess, okay, let's use the Y tensor. The local conformal flatness in 3 dimension corresponds to the cotton being 0, and in higher dimension corresponds to the Y tensor being 0, where the Y tensor is the full traceless part of the Riemann tensor. Okay, but turns out, okay, if you try to do the same procedure, I mean, or you give an ansatz for the family of vector fields as in Robinson, and you try to do a similar job with the Y tensor, nothing will work. So this is not a good choice. The right choice turns out to be this T tensor, which you don't have to remember the specific form of, but we are going to observe a bit how it's made. So the T tensor will be still a 3 tensor, like the cotton tensor, 3, 0, sorry. And what is different from the while is that somehow it keeps track of I will say the level set of the lapse. So you will see that the gradient of the lapse appears here. Okay, here I wrote it as a differential, but okay, it's the gradient. Okay, so it's given by a combination of Ricci and the gradient of f. Okay, this last part in green, I just wrote it down because originally this tensor has been, okay, I will say it later, but okay, we can define this tensor also involving the scalar curvature, but in our case, the scalar curvature will vanish because, so this will be 0, because this is equivalent to have that the Laplacian of f is 0, and sorry, this is equivalent to the static Einstein equation. Okay, so R will vanish. So we'll have only these two initial parts. And this T tensor actually turns out to be f, the lapse function times the cotton tensor minus the Y tensor computed on the gradient of. So it's a combination again of the cotton and the Y and the gradient of f. I wrote the whole tensor T, as you will see, if, sorry, with this additional term, because the tensor T is similar to the tensor D introduced by Cao and Chen in 2012 and 13 to detect rotational symmetry and classify steady Ricci soliton. I'm almost done with the time very steady gradient, right? I have to stop in 1 minute, right? I will try to stay in time. So, okay, I just want to mention that this has been employed in the steady Ricci soliton, which satisfies this equation, which is very similar to one of the, I mean, in the static Einstein equation, you will have an F appearing here. So this is different in somehow. And the tensor that I'm using is also cotton without the F appearing again, minus the while computed at the F. Okay. And okay, so what I'm going to say is, once you compute the divergence of okay, we compute the divergence of a family of vector fields that is similar of the 3-dimensional case, we will get the following formula, which now involves, I will call it green star, which now involves these two quantities. So the one that we had in the previous case, and then the T tensor. And it will be 0 only if and only if these two things vanish. Then integrating it on the whole manifold and using the divergence theorem, we will find the following formula. And choosing, okay, I will go very fast here. Choosing the parameters in two different ways. So in this picture, we see when this big F that we chose at the beginning is positive. And the boundaries of this area with respect to the parameters A and B define values of A and B, which gives exactly the two inequalities that we mentioned before. So somehow what the statement of the theorem that I mentioned before with the upper and lower bound on M is equivalent to have the divergence greater or equal to 0 for our parameter A and B, for different values of the parameter A and B. And the equality in this equation corresponds to having the divergence. As well corresponds to have these two quantities being 0. And one can show, okay, one can show that this system, so having these two quantities, gives rotational symmetry, and this is much more complicated than the three-dimensional case because one doesn't have, for example, the uniformization theorem for surfaces, and so one needs to work a bit harder. And yeah, just to have a very brief taste on the. Okay, no, maybe I can stop here, and if you're in, I will stop for questions, and we can talk about it if somebody is interested on how to use the T tensor being 0 to get the rotational symmetry. But yeah, this is the main idea of the whole theorem. I will stop here, I guess.
Yeah, thank you very much. Are there questions?
Yes, I have a question or two. First, this going beyond the three-dimensional case by including in the cotton tensor, so to speak, the traceless Riemann tensor, that is to say, the Weil tensor. Were you and your collaborators the ones who originated that idea?
Yeah, so the point, yeah, so I mentioned it very quickly. So the point is that originally so a similar tensor was introduced by Cao and Chen in the study of steady Ricci soliton, but it's not the same as you can. So there are similarities between steady Ricci soliton and the solution of the static Einstein equation because of the equation itself. So somehow you see that if I add an F here, I get one of the static equations. And that's why the tensor that they introduce with an F here will detect the rotational symmetry in our case. So somehow we were inspired a bit from then to get our rotational symmetry. I mean, it's a different problem, but somehow there is a communication between the static solutions of Einstein equation and the steady Ricci soliton.
Thanks. I think I understand. I have another question. Even in the static horizon or black hole case, is there any hope of extending your approach to the case of multiple components of the boundary? That is to say, the case of multiple black holes.
Yeah, so no, I don't think so. This will not work for many reasons. So first of all, one needs somehow to have. So there are many points where this is very difficult to get. So the one is the gravity. Sorry, the surface gravity of the horizon to be constant and having only one constant. Sorry, where did I write it? Yeah. So in both cases, the surface gravity here, we have it constant. So if I have multiple connected components, could be different constants. And then one can say, okay, maybe we assume that they have all the same constants, and this will solve this problem. But then, okay, then one has this problem in the three-dimensional case, for example, with Gauss-Bonnet here. So, for example, already in the three-dimensional case, using Gauss-Bonnet, you cannot close the argument because you will have the number of connected components appearing here, I think, or something like that. This K, or sorry, big N maybe being the number of connected components, and then the two inequalities don't close. And so somehow, okay, one can say, okay, if we assume this upper bound, sorry, so somehow, no, there is no, how can I say, reasonable hope, in the sense that it doesn't make sense to assume a lower bound with an N because it's not true. So yeah, so it doesn't work.
I think I understand, even in the 3D case with Gauss-Bonnet. Well, thank you very much for interesting talk.
Yeah, thank you.
Yeah.
Are there other questions?
So Albachiara, from what I understood, you said, okay, if we assume certain things, we get that there's a unique solution. Do you expect that this will happen even if you impose other conditions on the boundary? Or do you think you have the two situations in which this will happen? Wait, could you hear me? Oh, we can't hear you, Albachiara, I'm sorry. Well, or I can't, I guess.
I can hear you.
I could hear you too, Flor, but
Yeah, but I don't think oh, here, you're back. Yeah, I think you froze for a
Oh
second.
yeah,
Could you
I'm sorry. I
could
don't
you
know.
hear
I
my
think I lost
question?
connection.
I'm sorry. So my question was the following. Maybe let me just repeat. You found that if you impose these two conditions on the boundary, you get this uniqueness result. Do you think you have all such situations, or where there'll be other things you can impose on the boundary that still give you this uniqueness?
So okay, sorry, I have to think 1 second. But so this, if you see, so this formula that is appearing here, I hope. So these two inequalities, as we said, correspond. So if I have equality there, which corresponds just to this upper bound on the scalar curvature, I will have rigidity. So, okay. What I want to say, this is a pretty general form, written in a pretty general form, because we have any F0. The point is that, okay, we are assuming that F0 is constant, for example. And yeah, and then, okay, we are assuming this connection between the scalar curvature and the mean curvature. So I have a hard time understanding, like, I mean, it seems like very rigid in that sense, because one should have like similar relations. And if you think, yeah, so yeah, so I mean, I haven't actively thought about it, but it seems very rigid. And also in terms of physics, the very interesting objects somehow are those ones. But it's a very interesting question to try to generalize it as much as one can. Yeah. Yeah.
Thanks.
So to me, it seems the very okay. And also, I forgot this. For example, this condition will appear here, for example. So, sorry, there will be the norm of that appearing. So this will be something else that has to be encoded in the assumptions if one wants to conclude. Yeah.
Thank you.
Yeah, but it's interesting. Yeah, you're right.
yeah. Any other questions? I have just a short question about this very nice picture by the Event Horizon Telescope. So what does it exactly show? Maybe you can.
Is it appearing?
Yes,
yeah,
it's appearing. Yeah.
Yeah. So sorry. This is my way to explain to my friends when they ask me what I do, my research. So, and I like it, so I also bring it to talks. So the thing is that to see the black hole horizon, actually one sees the light around it, and so I will say, so one can say that this light that one sees is the trapped surface where the light is trapped and is not falling inside the black hole, which is exactly, I mean, in Schwarzschild it would be this R equal 3m, where the light is trapped. But then one can say, okay, but if the light is trapped, it doesn't reach the telescope. and it reaches the telescope just because the photon sphere is unstable. So somehow is not a perfect curve. The space around the black hole that they are taking the picture. I don't remember which one. Sorry, but so it's not a perfect curve, but it can be approximated by curve. But then it's a perturbation of curve, so the light will be actually escaping a bit and reaching the telescope. So that's that's the way I read, or like people could read this picture, I would say. So, and it's interesting because I mean it's a way of visualizing or seeing why photon spheres or photon surfaces are nice objects.
I see. Thank you. Okay. Any other questions? Then let's thank the speaker again.
Thank you for the interesting questions as well.